Welcome, integrated math superstars. There's something new about the classroom here. I'll leave that up to you to find it. Let's keep this going with the agenda. We'll take a look at another quick refresher on what's expected of you when you watch these videos. We'll continue to look at 1.4 examples in the efforts to solidify understanding that arithmetic sequences have a constant difference between consecutive terms. So for example, it'll always be adding 2 to the previous term. That's an example. We'll see others shortly. This was mentioned previously, just to reiterate, so that we are making the most of our time in class and also with these videos. Make sure that you're copying down all of the work that's shown or completed. Use the resources on Blackboard if you like to print another outline, even though you already have one in the textbook you picked up at the beginning of the year. Make sure to pause and rewind if you get stuck on something that doesn't quite make sense. And if you practice all of these things, the material comes easier to you. You're able to ask more questions in class, and we're able to make the most of our time. Sounds good, right? Don't you think? Let's see what's going on here. For the ready, we're being asked to evaluate the given equation for the indicated function values. We've already done something like this in 1.4, dealing with Scott's push-ups, where we had that table and we had to evaluate at select values as time went on. So we're kind of doing the same thing here, but each of these has select values and select equations that we have to give respect to. So I'm definitely going to talk about problem 1. I'll definitely talk about problem 4. And definitely problem 5 to help you get started. So I know that if this function here, f of n equals 5n plus 8. So f of 4, let's rewrite most of the equation. And so instead of n, what am I now putting in place? Hopefully you're saying 4. And what's 5 times 4? Definitely 20. Don't forget the 8. And so what's 20 plus 8? Hopefully you're saying 28. Pause the video, try the next problem. I don't think these problems are too bad. If you've been working hard so far this year, you should be just fine. So I know that I'm evaluating now -2. So instead of n, putting -2. 5 times -2 gets us -10. If we add on 8, starting with -10, sometimes the visual helps here. If I start at -10 on the number line, and I hop once, twice, 3 times, 4 times, 5 times, 6 times, 7 times, 8 times, I'm at -2. It's a -2. Boom. Hopefully you got that. For 4, a little challenging because our function f of n is equal to -n. It's kind of odd to just see n on its own, but follow along with me here. Instead of n, I'm going to now put in parentheses with 9. So think of this as if I'm rewriting n, but since there's a negative sign out here, I'm going to give respect to that and use parentheses just because I'd like to section off what number I'm plugging in. And I see students trip up a lot here, not being too sure how to rework the answer. So I would think of this as if you have an imaginary -1 in front of the parentheses. And if you rewrite this, -1 times 9 gets you -9. Boom. Next one, f of -11, a little tricky, but that can't stop you. Just follow along with the step that I did before. Put in that imaginary 1 at the beginning, then treat it as if it's multiplication. -1 times that -11. What happens if we have a negative times a negative? Hopefully you're saying it becomes positive. And then 1 times 11 just leaves you with 11. Boom. For 5, instead of n, I'm now putting 2. But we don't just want to leave that answer there, do we? 5 squared, I could rewrite that as 5 times 5, and then evaluate that to just 25. Then how about for f of 3? Instead of n, I'm putting 3. I can treat that as if it's 5 multiplying with itself 3 times. I kind of see a similar pattern here where we already did 5 times 5. We know that's 25. So what's 5 times 25? We have 5 quarters. How much money is that? Hopefully you're saying 125. Boom. Simple. Pause the video if you don't have all of this just yet, because I'm about to erase it. Let's move to the set, where here we're finding terms for a given sequence. So we already have a pattern going. We're being asked to talk about the common difference, the recursive formula, which calls back to one of the previous functions that starts from the get-go, and then continue to talk about an explicit function. All right, let's do this. Common difference, I think, is the easiest thing to do. So what's the difference from 3 to 8? And is that the same difference from 8 to 13 if we're moving towards the right? Well, if I start at 3, and if I add 5, that gets me to 8. And if I go to 8 and then bounce to 13, I add 5 more. Is this consistent with the other numbers? Sure is. So we say our common difference is 5. And so every time we move to the right, we're adding 5 more. So 23 plus 5 gets us 28. 28 plus 5 gets us 33. 33 plus 5 gets us 38. Feeling great. For the recursive function, and this is going to tie into how our first number is the first term, not the 0th term. That's important to make note of because this is going to kind of feel similar to when we dealt with the push-up problem and we had the first term and the second term. So just to work in that mindset, I'm going to label this as the first term, second term, third term, fourth term. And so the very first term here is f of 1, which is equal to 3. And then how does that change as we move to the next one? Think about that in words. Like, what does the next number equal in comparison to the previous one? Well, it's as if we take the previous number and then just add 5, right? Because we said the common difference was 5 as we move towards the right. So if we use those words, next we normally denote as f of n. And if we're going for the previous number or term, we call that n minus 1. And then notice that we add 5 at the end. So we need 2 things to mention this recursive function. We need f of 1 is equal to 3, and f of n equals f of n minus 1 plus 5. So notice I worked from the very first term. I started to write down words that expressed what was going on, and then I fell back on how the function should look, or equation. Sorry, function. So those 2 work. If we are aiming for our explicit function, we know that we have our first term here, but do we have a term before it that's not written? Hopefully you're saying yes, where the 0 term would just be deducting 5 from 3, so this would be negative 2. So in this case, recall that the explicit function is going to start at the 0 term, and if we keep that going, it's as if we keep adding 5, depending on how many times n shows up. And what's cool is that we can try this out and double check that it works. So if we wanted to do f of 1, this should be equal to -2 plus 5 times 1, and the outcome's 3, so that's good that it works for that. So that's our explicit function. We were also asked to circle where we see the common difference. So I see 5 right here, 5's right here. Hope that helps. Concluding with the graphing and reading this graph here, we have a mountain climber, Olaf, climbing this mountain beginning at noon, ending at 4. What's Olaf's elevation at noon? Well, noon is another way to write 12 p.m. So what's the height of this dot right here? Well, let's think about how this is scaled. We start at 1,000. We then hit this notch, this, and then 5. So it's as if every time they're adding 1,000 feet. So if we're one notch below 10,000, what's this height? Hopefully you're saying 9,000 feet. Hope that this video was helpful. If you have any questions, bring them to class. Thanks for watching.